the YouTube channel, the only one. I'm kidding. All right. Okay, so far we looked at hydrohalogenation with HCl, HBr, and HI, and now we're going to talk about acid catalyzed hydration. So if you remember, hydration is where you take, you have your alkene and then you treat it with water, okay? And so on one carbon you add a hydrogen and on the other you add a hydroxyl. Now that's the simplest possible example I could give you, is something like that. But a better example is what's shown here, is because we need to have a catalytic amount of acid in there. And so it follows Markov-Nakhov-Regio selectivity, right? The rich get richer. This carbon has a proton on it. And so now it's got 2 protons on it, right? After you add the water to it. But the water, you add that with a catalytic amount of acid. Now, why do we write H3O plus here? And then why do they write H2O and H2SO4 here? So this is something I think I've explained to you a few times, but I'll do it one more time. And that is, if you mix sulfuric acid with water, you're going to have an equilibrium, which is going to lie hard to the side of the products, right? Which are going to be hydronium plus the hydrogen sulfate ion. Why is that? Because sulfuric acid is a pK of -9 and hydronium is a pK of -1.7. So the equilibrium is going to lie to this side. So when you mix sulfuric acid and water, what you actually have is H3O plus. It's a solution of hydronium. And so that's why we write H3O plus. We don't write out sulfuric acid in square brackets plus water, but you can do that if you want to. It's just denoting that sulfuric acid is your catalyst. And so there you go, our Markov-Nakhov addition. Now, a little bit more about the mechanism and the fact that it passes through a carbocation intermediate. If you look at the relative reaction rates here, right, for each one of these reactions, well, if you were to do this reaction, the addition of of water across ethylene, you would end up with a primary carbocation, right? That would proceed through a primary carbocation, and we know that those are really unstable. If you did it with propylene, it would go through a secondary carbocation, and if you did it with isobutylene, you'd go through a tertiary carbocation. And you can see that with the tertiary carbocation, the reaction rate is much, 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 much faster than with a secondary or a primary. And so this is just some evidence that proves the mechanism. Now, if we look at the mechanism, it's very similar to that of the hydrohalogenation reaction. The first step is a proton transfer, and we form the most stable carbocation, right? You can see that you form a tertiary carbocation here. If the proton was added to this carbon, then you would have ended up with a secondary carbocation, right? That's why we get Markov-Nakhov addition. The next step is a nucleophilic attack of water, but we have an extra proton transfer, don't we? Because after the nucleophilic attack, we end up with an oxonium ion, and that oxonium ion has to be deprotonated in order to restore neutrality and give us our alcohol. So there you go, Markov-Nakhov addition of water across an alkene. Give me a thumbs up if you follow me on that. That the addition of acid catalyzed addition of water across an alkene is Markov-Nakhov, and this is the mechanism. Good. So you can imagine that since we proceed through a carbocation intermediate, and a couple of slides ago, you told me that a carbocation is sp2, therefore it is trigonal planar. That means it's flat. So the nucleophile, the water, could come in from either face of the molecule. So if you can form a chiral center, like we do here, you'll end up with a pair of enantiomers, right? You end up with a 50-50 mixture of enantiomers. Now, I just want to back it up for a second here, because something that I feel, or something that I didn't share with you is this concept here. Do you guys remember Le Chatelier's principle? If you're rolling your eyes and saying, yeah, I never stop hearing about it, right? Because you hear about it in Gen Chem 1, Gen Chem 2, and now it's here in Organic 1. Well, it's a very important principle, and we can actually use Le Chatelier's principle to determine whether we want to get the alkene or the alcohol. So here's how we use Le Chatelier's principle. If you do this reaction with just a catalytic amount of sulfuric acid, so a dilute solution of sulfuric acid and more water, right? If you elevate the amount of water, that's going to drive the reaction forward towards the alcohol. Conversely, if you do the reaction in concentrated H2SO4, so there's very little water, and you remove the water from the reaction, that's going to drive it towards the alkene. And so this is one of those situations I feel like where students have to actually think about this quite a bit to understand what's going on here. So with dilute sulfuric acid, we're going to get the alcohol, and with concentrated sulfuric acid, we generate the alkene. You got to either memorize this or try to figure it out, or maybe you just understand it by hearing it the first time, which would be great. But these are two reactions that we're going to use quite a bit, because once you step into organic 2, the first thing that we study is alcohols in that class, and we use this reaction or these reactions quite a bit in that chapter, right? Because you end up making an alcohol or dehydrating an alcohol. Okay, so very, very important. I'm going to put a star by that. Okay, very important concept, Le Chatelier's principle. So a little bit of water is going to drive us towards the alkene, and a lot of water is going to drive us towards the alcohol. All right, so we've covered the stereochemistry and that we get the RNS product because we proceed through a carbocation. So with all that in mind, let's see if we can draw a mechanism here. Now, if you look at this mechanism, if we study these two this carbon has got 2 protons on it, and this carbon has 1 proton on it. So is this Markovnikov or anti-Markovnikov addition? Well, it's not really abundantly clear, right, the way that it's drawn. I mean, we would start with Markovnikov, but what must be happening here in order to get this final product? Can anybody see it? Sean, I couldn't give you a bigger thumbs up. Exactly. Yes, there's a rearrangement going on here, isn't there? And how are you going to figure that out? By drawing the mechanism. So let's do it. So let me just draw a hydronium ion here. So just bear with me here. So let's draw a hydronium ion. Let me see, I'm going to need enough room here to solve the problem. So we'll draw an H3O plus ion. And we'll put our arrows here. And we're going to get a proton transfer. So we're going to grab a proton. I didn't put the positive charge on my oxygen. There we go. All right, we fixed that. So now we're going to end up with this. Okay, so we end up with this guy here. So we end up with a secondary carbocation. And we know that that can undergo a hydride shift from this proton over here to give us a beautiful tertiary carbocation. All right, give me a thumbs up if you're with me on that part of the mechanism thus far. Okay, awesome, awesome. Okay, so now we have water, which is going to come in as our nucleophile. So let me just draw a water molecule. And that's going to do this, nucleophilic attack. And then we're going to form an oxonium ion. So that's going to look something like this. Son of a gun, is this a joke? Okay, I just want to make sure it didn't erase everything. So let me get started again. Here we go. Thanks, iPad. I really appreciate that. Okay, so first step is a proton transfer. Go. We end up forming a secondary carbocation. And we get a proton shifting. So this is a hydride shift. And we make a tertiary carbocation. Then water comes in as our nucleophile. And then we form an oxonium ion. Looks like this. And then for the last step, oops, come on, there we go. For the very last step, water is going to come in and behave as a base. It's going to peel this proton off, and we end up with the alcohol. Phew, there we go. All right, got it, and it didn't Rearrange. So, what's going on in this part of the mechanism, right? If we look at the first step is a proton transfer. This step is a nucleophilic attack. This step is a proton transfer. But what's occurring here? This is a rearrangement because we proceed through a carbocation. So the question we're going to address next is this. Is there a way to avoid this? Avoid this. And the answer is yes, there is a way to do that, okay? And it's using a reaction called oxymercuration demercuration. So I'll put yes, C, chapter 8.7, okay? So we're going to go to the next section, which deals with oxymercuration demercuration, okay? It's just a way to do the Markovnikov addition of water across a double bond, but we avoid carbocation rearrangements. That's all it is. So if we were to go back to the problem that we saw before, let me show you how it would work. So if we had our alkene like this, and you wanted to add the water across that in a Markovnikov fashion, we do it in a couple of steps, okay? The first step is going to be HgOAC2, so that's mercuric acetate, and you put it in water as your solvent. And then the second step is you treat it with a reagent you've never seen before. This is called sodium borohydride. So it's 2 steps, okay? And that would give you the Markovnikov product with no rearrangements. Okay, now I'm getting way ahead, right? I'm just showing you the whole thing before we get there. But it's important to note that it's 2 steps, and it involves mercury. And mercury is, kind of a dangerous element to work with. And so we actually try to avoid this reaction when we can, but sometimes we just have to do it. So let me show you a little bit of background on this. And before I get into all the nuts and bolts, I will not ask the mechanism, okay? I'm going to put that right here, okay? Will not ask the mechanism of oxymercuration and demercuration. Will not ask mechanism. In fact, you know what? I should delete this and just put this will not ask mechanism. I should put it over the oxymercuration part because there's no mechanism provided for this. For demercuration, there's no mechanism even shown in the textbook. But if you think about like every single person who's hearing the sound of my voice right now, whether you're in class or watching this video, I really would be skeptical if you made it this far in your education, if you stayed in school this long without liking some subject at least some point in your life, right? You probably took a class at some point and you said, I like that class. And usually when a student likes a class, it's because they understand the material very well. And so even though I'm not going to ask you this mechanism, the idea is this. The reason I'm going to talk to you about it a little bit is because the more you understand something, the easier it becomes to just rationalize it in your brain, and it usually sticks there a little bit better. So here's what happens. You have this reagent, which is called mercuric acetate. That's this guy right here, okay? And for that, we just use the molecular formula, which is HgOAC2. Now, if you're like, what's an AC, okay? An AC group, so AC stands for acetyl, which is this. Okay, so if you have OAC, the oxygen is this oxygen here. So that's an OAC group. So it's an acetyl group, okay? So what happens is the mercuric acetate, or you can call it mercury 2 acetate, doesn't matter, but the mercuric acetate undergoes this fragmentation to give you a mercuric cation. So you're like, wow, when was the last time I saw a mercuric cation? Well, you haven't, okay, until now. But you can imagine this is a good electrophile, right? It's got a positive charge baked into it, so it's it's hungry for electrons. And so what's going to happen is, you remember how the pi bond could act like a base? Well, or it can act like a nucleophile. Well, you can see that the pi bond, when you put it in the presence of that mercuric cation, so this is the mercuric cation that we saw on the previous slide, so mercuric cation, it acts like an electrophile and attacks it, okay? And then you end up making this thing here, which we call a mercurinium ion. Okay, so you get a mercurinium ion, and you can see that there's 2 contributors to the resonance structure, and one of them is like this 3-membered ring. And so this mercurinium ion, the idea is this. the mercuronium ion is never going to rearrange. And that's why you get Markovnikov addition and you avoid carbocation rearrangements. Now, if you're wondering, why does the bond between carbon and oxygen occur at the more substituted carbon? Like, why does it occur at this carbon in green and not in this carbon in red? It's because when you get the nucleophilic attack by the water, it passes through the more substituted carbon. So this one here, right? This is the more substituted carbon. It goes through it because you have a partial positive charge on the more substituted carbon. What would you rather have, a partial positive charge on tertiary carbon or a secondary? It would be tertiary. And so that's why it's a Markovnikov addition. Now the second step, the demercuration. So that's, for that we use sodium boron hydride. So this is the demercuration step, okay? There's no mechanism provided for that whatsoever. And the reason why is that it's believed to occur via a free radical mechanism. So that doesn't involve pairs of electrons, that involves single electrons moving around. I'll just give you a clue. It's not even in chapter 10. It's not shown anywhere in our textbook. So you don't have to worry about that mechanism at all. And again, the only reason I showed you this is just to provide some background or some context for the reaction. So what's the conclusion, right? What do you need to know as a Chemistry 3101 student? I would say kind of what's shown here is if you do the acid catalyzed reaction, so that's the one on the top, and it's going to proceed through a carbocation. If that carbocation can rearrange, you're going to get what? You're going to get a mixture of products, okay? If you do oxymercuration, that's this step, followed by demercuration, so it's a two-step process, you get no rearrangement and you get Markovnikov addition. So I'll put here Markovnikov addition. Pretty cool reaction, huh? Anyhow, so those are kind of your two options. Now, just to put this bug in your ear, if you're sitting there thinking, well, I'm going to use oxymercuration, demercuration for everything, you know, so I can always avoid carbocation rearrangements. Well, hold the phone. It's not really the best choice. If you have a reaction where you're not going to get a carbocation rearrangement, you should not choose oxymercuration, demercuration. Why? Because it's bad for the environment. And if you're like, oh, are you kidding? No, I'm not kidding. I'm dead serious. It's mercury is not good for the environment. It's ugly to mess around with. I've used it many times. I don't like it. Okay, and that's not just my opinion. Okay, that's most organic chemists' opinion. They don't want to mess around. I'd say all organic chemists' opinion. Nobody wants to mess around with mercury. So there you go. So for section or question 8.16, I'm going to try to make it as simple as possible. Let's just do A for now. It says predict the product for this reaction and predict the products if you did an acid catalyzed reaction. So look, if we did oxymercuration, demercuration, all we get is Markovnikov addition. So all you would get is this, the rich get richer. You form a chiral center here. And so that's it. This is the only product that you get. And then, of course, this would be racemic. So I'll put here racemic, right? Are you with me on that? Just a Markovnikov addition. That's all we would get. That's with oxymercuration, demercuration. If we were to do acid catalyzed hydration, let's take a look here. And I'm not going to draw the entire mechanism. I'll just draw kind of a short version of it here. If we have H+, which comes from our hydronium ion, like this, okay, like that, what's going to happen is we're going to get a proton transfer like this, and we're going to form this carbocation like that. Now this is going to undergo a methyl shift to give you a more stable carbocation, which is going to be this. And so you're going to get a mixture of products, aren't you? Right? You're going to get after nucleophilic attack and proton transfer and nucleophilic attack and proton transfer here, you're going to get a mixture of this compound, the same compound we got from the oxymercuration, demercuration, and of course that's going to be racemic. And you're also going to get some of this tertiary alcohol as well. All right, so you're going to get both of those compounds. And there you have it. And you can try the same thing for B. I encourage you to do this one at home. But there you go. That covers the first one. Well, in the interest of time, let's cover one more reaction before we take another short break here. And this is, if you're wondering, is there a way to do an anti-Markov-Nikov addition of water across a double bond? The answer is yes, right? So far, we covered the anti-Markov-Nikov addition of HBr, right? We said if you had an alkene like this, you could treat it with HBr and peroxides, and that would give you the anti-Markov-Nikov product, which would be this. So anti-Markov-Nikov. However, if you want to do an anti-Markov-Nikov addition of water, okay, it's a two-step process. We call this hydroboration. Okay, it's got a long name, hydroboration oxidation. Hydroboration is the first step. Oops. And for that, we use this molecule called borane, and we make a complex with it in THF, and I'll explain what THF is in a second. In the second step for the oxidation, we use hydrogen peroxide and sodium hydroxide. Okay, so again, it's two steps. So what's going to happen is you get anti-Markov-Nikov addition of water. First step is hydroboration. I'll explain what BH3THF is. And second step is hydrogen peroxide and sodium hydroxide. Again, this is a mechanism I don't ask you to memorize, or I've never asked about the mechanism, maybe in a homework, and that would be about it. If you take organic chemistry for chemistry majors at UCCS, we do go into the details of this mechanism, but in 3101 and 3111, we do not. However, it is covered in the textbook. And so not only is hydroboration oxidation regioselective to give us the anti-Markov-Nikov product, it's actually stereoselective too, because you're adding two atoms, aren't you? You're adding you're adding two groups, I should say, a hydrogen atom and a hydroxyl group. And what we get is we get what we call syn addition. So SYN. And syn addition means added to the same face of the molecule. Face of the molecule. Okay, this is a question that always shows up on the final exam. If you were to take a compound like this and treat it with borane THF followed by hydrogen peroxide and sodium hydroxide, what are the products? And they give you all four of these, and they say is it A, B, C, D, A and B, C and D, A and D. All right, they give you all the possible answers, and you need to know that not only do you get the anti-Markov-Nikov product, right, the hydroxyl gets added to the less substituted carbon, but you also need to know that the hydroxyl and the proton get added to the same face of the molecule. Either get two dashes or two wedges. If you draw the proton and the hydroxyl as a dash and a wedge like this on opposite faces, this is what we call anti-addition, opposite faces of the molecule. You do not get that. You do not get those products. Okay, so it's regioselective and that it's anti-Markov-Nikov, but it's stereoselective and that it's syn addition. The hydroxyl and the proton, the hydrogen atom, are added to the same face of the molecule. So let's take a little bit of a look at this borane reagent. And if you look at borane, so this is BH3, it's got a name. You can call it boron trihydride. Well, don't do that. It's got a name, which is borane, okay? And borane is sp2 hybridized. The boron is anyhow. So it's got an empty p orbital on it. And so you can imagine it makes a good Lewis acid, a good electron acceptor. Now, if you just leave borane by itself, BH3, it will react with itself and it forms a dimer that we call diborane. And it forms this kind of two electron, three center bond. And I'm not going to ask you about this, but sometimes in the MCAT study guides and the ACS, they'll put B2H6. And all you really need to know in this class is if you see borane THF, which is what we are always going to use in this class. If you look at an ACS study guide or an MCAT, sometimes they'll put B2H6, and it does the exact same thing. Okay, it does the exact same thing, so don't really stress about that right now. But if you're wondering, what's this BH3THF, and this is actually incorrect, it should have the dot like right in the middle. It should say BH3 dot THF. So what happens is that the borane, the BH3, acts as a Lewis acid, and THF, and that stands for tetrahydrofuran, acts as a Lewis base, right, an electron donor, and you form this complex. So this is what we call a complex, and you would have studied these a little bit in general chemistry too. So this is the borane THF complex. And I'm not going to go into a whole ton of detail about the borane THF complex right now. But the idea is that we get anti-Markovnikov addition. Now, why do we get anti-Markovnikov addition? Well, the real reason is shown right here. Okay, if you're like, what's the answer? The answer is this. Okay, there's kind of a double answer, really. What happens is when you have the initial reaction between borane and the double bond, is what happens is you end up adding a hydrogen to the more substituted carbon, and then the boron gets attached to the less substituted carbon. You can see why that would be. It's because of sterics, right? The hydrogen goes to the more substituted carbon because it's just bulkier. And the boron gets attached to the less substituted carbon. And that's kind of one of the answers, is just based off of sterics. And then there's another answer which rationalizes it by an electronic effect. And I think that's shown, where is it? It's shown right here. So this is showing the sterics, okay? More crowded versus less crowded. And the electronics is shown, oh shoot. Yeah, okay, so it's shown here. I didn't even notice it before. So you have a partial positive charge built up on the more substituted carbon. You know what? It's summertime. I'm going to leave that as an FYI. I'll tell you why. It's because I will not ask this mechanism. Let me show you. It's all the way. I will not ask this mechanism. I'll even write it on the slide. Will not ask this mechanism. Okay, but you see the whole thing is shown here, the entire thing, and I'm not even going to go over it with you. Okay, all you need to know is the regioselectivity and the stereoselectivity. If you want to go through this, I'll leave it as an FYI, but I'm pretty sure that everybody's got enough information in their brain by now that they don't need to go over this in detail unless they really want to. And so again, what you need to know is anti-Markovnikov addition, so that's the regioselectivity, and stereospecificity is that the proton and the hydroxyl are added to the same face of the molecule. However, if you can form a chiral center, one chiral center, you're going to end up with a pair of enantiomers, wouldn't you, right? So we have to take that whole idea of chirality into account when we're looking at a hydroboration oxidation reaction. And if you're forming two chiral centers, in that case, you form a pair of enantiomers. You form a pair of enantiomers, I guess. Anyhow, so with all that in mind, why don't we try a practice problem? So this is question, it's just a practice problem I have in the slides here. And the answer is shown. So remember, we're going to get anti-Markovnikov addition. So what I'll ask you is this, is if I highlight this carbon in yellow and I'll put this one in red, which one of these carbons is going to take the hydroxyl if I'm doing an anti-Markovnikov addition? I'm trying to flip it around and try to test you on it. Which one is going to take the hydroxyl? It would be yellow or red? It's going to be the yellow one, exactly. So we get syn addition. Okay, so what's syn addition? It means that the hydrogen and the hydroxyl are added to the same face of the molecule. So we're going to end up with this. So we don't touch this stereocenter. So I'm going to put the proton, I'll put the hydroxyl going down, okay, like this. And that would mean that this proton is going down and this methyl group is going to be going up, like that. Now, can I get the other syn product as well? Let's see here. If I draw it like this, remember, I don't touch this stereocenter. If I draw the hydroxyl going up and I draw the proton going up like this, then I'll have the methyl group going down. Could anybody tell me the relationship between these two compounds? This would be a pair of what? You have to go back to the days of chapter 5 to answer this problem. What kind of pair of compounds do I have here? Yes. Yes. Pair of diastereomers. Heck yeah. Diastereomers. Yes, excellent answer. Everybody nailed it. Awesome. So you see the answer is here. We end up with a pair of diastereomers because we already had a chiral center in the molecule, and the chiral center is untouched, right? We have no effect on that chiral center whatsoever. So that brings us to the next practice problem, which asks us to provide the products for each of the following reactions. So we're going to get anti-Markovnikov addition for each of these.